Hey everyone, it's Justin again. In the last lesson, you learned how sine, cosine, and tangent values can be determined from points on the unit circle. Now, let's fill out the unit circle in full to make this tool even more useful. By the end of this lesson, you should be able to use the unit circle to determine trigonometric values for any angle from 0 to 360 degrees. First, we'll extend the idea of sine, cosine, and tangent past 90 degrees. Next, we'll fill in all remaining angles and coordinates on the unit circle. We'll explore how to create the unit circle from scratch, and then you'll use the completed unit circle to practice some examples. Let's do a quick review of the meaning of sine, cosine, and tangent. The sine of 30 degrees is the y-coordinate of the point at 30 degrees on the unit circle. That's 1/2. This cool trick, taking the y-coordinate to find the sine of an angle, came from the definitions of the trig functions. They are ratios of the sides of a right triangle from the perspective of that angle. SOHCAHTOA helps us remember which ratio goes with which trig function. The sine is the opposite over the hypotenuse. Recall that the hypotenuses of the triangles we drew this way were always 1. And since the opposite side was always just the y-coordinate, the sine is just the y-coordinate over 1. So the sine is the same as the y-coordinate of the point on the unit circle circumference. We went over this last time, but here's where we're going to shake things up. There's a question we can ask ourselves now that makes things really interesting. If the sine is always the y-coordinate on the unit circle, does that mean the sine of 90 degrees is 1? If we're thinking of the sine as the y-coordinate, it seems pretty obvious. The y-coordinate of the point at 90 degrees is 1, so the sine must be 1. But can you make a triangle that proves this, like we did for 30 degrees? Let's start with this 30-degree triangle on the unit circle and see what happens when we try to increase that angle up to 90 degrees. Here's 45, 60, 75, 85, 89, 90? We don't even have a triangle anymore. It's completely thin. It's just a line. So why did this happen? It's because we've been making these triangles with the x and y coordinates of the point at a given angle. But the x-coordinate of this 90-degree point is 0. We can't make a triangle where one of its sides is length 0. Also, consider the unit circle has way more than just 90 degrees. It has 360 degrees. But you also can't make a triangle with a 200 or 300-degree angle. So how can there be sines, cosines, and tangents if we can't make a triangle where we can use SOHCAHTOA? So even though it doesn't make sense with our original interpretations of sine, cosine, and tangent as ratios of triangle sines, we could find these values at any angle on the unit circle if we switch to primarily thinking about cosine as the x-coordinate, sine as the y-coordinate, and tangent as y over x. Now we're no longer stuck with only the first quadrant. There is, however, one interesting situation we should talk about before we go any further. What's the tangent of 90 degrees? Well, the point at 90 degrees is 0, 1, and the tangent was the y-coordinate over the x-coordinate. So that's 1 over 0. Boom! Easy! Solved! Oh, wait! We've divided by 0, and that's not allowed. Turns out the tangent of 90 degrees is actually undefined. Not just on the unit circle, but in general. So the answer is undefined. It sounds like an excuse, I know, but that's actually the valid mathematical response. So keep that in mind for later. All right, now that we know we can use the whole unit circle, let's fill out the rest of it. You've seen this unit circle before with the 3 lines in the first quadrant denoting the 30-degree, 45-degree, and 60-degree angles. There are actually 3 important angles like that in each quadrant. This unit circle is very nice and symmetrical, which will be helpful for multiple reasons. The first way in which the symmetry is useful is for finding the values of these angles. Just like the 30, 45, and 60-degree angles in the first quadrant, all angles on the unit circle are 30, 45, or 60 degrees away counterclockwise from the nearest multiple of 90 degrees. For example, think about this point in the top left. We're measuring in standard position, so this angle includes these 90 degrees. Then we go 30 more degrees to get to the point we want. So this angle is 90 plus 30 degrees total, or 120 degrees. The next angle would be 45 degrees more than 90, or 135 degrees. And the angle after that would be 60 degrees more than 90, or 150 degrees. Using this property, pause the video now and see if you could figure out what the rest of the angles would be around this unit circle. These are the remaining angle measures. Now we just need to find what the coordinates of their points are. Let's start with the 120 degree point again. This time, to find the coordinates, we actually don't need any calculations at all. We can again make use of the unit circle's symmetry. Recall how we found the 60 degree coordinates. The 120 degree point is just a reflection of the 60 degree point across the y-axis. When plotting either of these points, we travel half a unit horizontally from the origin, and square root of 3 over 2 units vertically. The only difference is, the triangle for 120 degrees goes half a unit to the left, which is the negative x direction. That means they have the same coordinates, but the x-coordinate, 1/2, is negative. The coordinates for the 120 degree point are negative 1/2, comma, square root of 3 over 2. In fact, all of the points of the second quadrant have a negative x value, but they're otherwise the same coordinates as their reflection over the y-axis. 135 degrees has the same coordinates as 45 degrees, but with the negative x coordinate. And 150 degrees has the same coordinate as 30 degrees, but again, with a negative x. Pause the video now and see if you can figure out what the rest of the coordinates would be around this unit circle. Is this what you got? Points in the third quadrant should have negative signs on both coordinates, and in the fourth quadrant, they should have positive x coordinates but negative y coordinates. The strategies we use to fill out the unit circle are worth remembering. If you ever need a unit circle but you don't have one in front of you, you can use the left-hand technique to recreate the first quadrant. At 30 degrees, we have 3 fingers above and 1 below. So those coordinates are square root of 3 over 2, comma, square root of 1 over 2. And of course, the square root of 1 is just 1, so 1/2. At 45 degrees, we have 2 fingers above and 2 below. So those coordinates are square root of 2 over 2, comma, square root of 2 over 2. And at 60 degrees, we have 1 finger above and 3 below. So those coordinates are square root of 1 over 2, comma, square root of 3 over 2. Again, square root of 1 is 1. This works because the number of fingers above correspond to the cosine, which is also the x-coordinate, and the number of fingers below correspond to the sine, which is also the y-coordinate. You could also find these coordinates by creating special right triangles like we did the first time, but the left-hand technique is faster. Once you have the coordinates of the points in the first quadrant, you can use those points to label their reflections in the other quadrants. When you have a finished unit circle, you can find all of the most important sine, cosine, and tangent values in no time at all, because these rules, cosine equals x, sine equals y, and tangent equals y over x, are true for any point on the unit circle. Let's do some examples to see how we can use this diagram. Use the unit circle to find the cosine of 300 degrees. Okay. Remember that the cosine of an angle is the x-coordinate of the corresponding point on the unit circle. We check the point at 300 degrees, and the x-coordinate of that point is 1/2. So, the answer is 1/2. Questions like these are why having the unit circle is so helpful. Here's another example. Find all possible values of theta between 0 and 360 degrees such that the sine of theta equals negative square root of 2 over 2. To start, note that the question implies that there could be more than one angle that gives you a certain sine value. In fact, most values of sine, cosine, and tangent have more than one angle that gives you that value. So let's use the unit circle again. The sine value is negative, which tells us that the y-coordinate is negative since sine is the y-coordinate. So the angles we're looking for should be below the x-axis. There aren't too many points to search through to find the right y-coordinate. The only angles that give us points with y-coordinates of negative square root of 2 over 2 are 225 degrees and 315 degrees. That means both of those angles have sine values of negative square root of 2 over 2, so they're both possible values of theta. Here's one more example for you. If the tangent of theta is undefined, what is one possible value of the cosine of theta? To answer this question, we need to know how the tangent ratio can end up being undefined. Tangent is the y-coordinate over the x-coordinate. So what could happen here that would cause this to be undefined? What number from this unit circle could cause problems if you put it in the wrong place in a fraction? Answer is if the denominator is 0. That's the only way this fraction could end up undefined. So we're looking for points where the x-coordinate is 0. The points at 90 degrees and 270 degrees both have x-coordinates of 0. So 90 or 270 are possible values of theta. So a possible value of the cosine of theta is 0. At both 90 and 270, the x-coordinate is 0. And that matches what we've been thinking so far. Cosine was the x-coordinate, and we were looking for points that had an x-coordinate of 0. That means the cosine had to be 0. In this lesson, we extended the unit circle from 1 quadrant to 4. As you move on to practice for this topic, we've provided you a PDF of a completed unit circle. You can use this while working through the practice problems, so make sure to have that on hand. The unit circle will be required to answer some of those questions. If you'd like some more practice, you can also try creating your own unit circle using what you've learned today. See you next time.